So vectors and vector spaces. Most of us remember this, of course, but a vector is simply a mathematical structure that has two attributes. It has a magnitude, which is the size, but also a direction. If you take two dimensions and look at x and y as the two axes of this two-dimensional surface, let's say, a vector would simply be something, for example, that goes from 0, 0 to any point x, y. And if you plot it on a piece of paper, which we will in a few minutes, we would see a vector which was drawn out as a line with an arrowhead going from 0, 0 to these points x and y. Vectors, depending on the number of these elements that they have a concept associated with them called dimension, which could in general be some number n, and in this case it's two dimensions, x and y, and the elements of the vector itself can be real or complex numbers in the most general case. A scalar is a quantity that has no dimensions, it's just a value, it's a number, and it's an element of each of these positions, in this case a two-dimensional vector. Okay? So vectors and scalars are useful things to remember as we move forward, and many times when we want to represent information from the real world, such as audio signals, video, radar, many different types of signals, and these are usually patterns that repeat over time, represented as periodic functions, then we can think of writing the signal as a vector with elements x1 through xn. x1 is the sample of this vector representing the beginning of a period, xn is the sample representing the end of a period, and intermediate values xi are values between the beginning and the end of the period. And we will be coming back to this way of thinking about signals. Instead of writing out a full signal, a sampled vector representation as a useful way of manipulating them when we need to in future lectures. So here is an example. You have here a signal, and the portion here which I am pointing to with the red dots on it is one period. This is the beginning, the origin, let's say, and that's the end. And so you have a set of samples here, x1 through xn, that capture the signal. This is, of course, the very commonly used sine function. Vectors have their own algebra that goes with them. So you can create new vectors from given vectors. So you can add two vectors. That's the most basic thing you can do. So given, and we are using boldface to represent vectors and plain font that's not bold to represent scalars. So if we think of a vector with n elements A, another vector with n elements B, the vector sum of A and B is taking each element A1 and B1, adding them, and that gives you the entry, which is the first entry in the sum vector A plus B. Similarly, if you go to the last element an and then the last element bn, an plus bn would be the last element, and also you would have several such other elements in the middle. That's how you add two vectors. Now there's something called scalar multiplication. I'm just defining terms for us. So L is a scalar, and if you take the scalar L and multiply it by the vector A, the resulting vector would be L times A1 plus L times A2 plus L times, and so on, to L times An. A linear combination, when L1 and L2 are two scalars, L1 times A1 plus L1 times A plus L2 times B is a linear combination of A and B. That's called a linear combination, where you take a vector, multiply it by a scalar, take another vector, multiply it by a scalar, and then add the two vectors together. These are all straightforward concepts, but the big one that we have here that we need to remember is span, and that's very useful as we move forward. So I'll spend a couple of minutes on it. So given a bunch of vectors, a set X of vectors, the set of all possible linear combinations of vectors of X is called a span. So you can take every possible combination of vectors from X and any kind of a scalar from the set that we are allowed to choose from, and the resulting set, which can be quite large, is called a span of X. So a span given a small number of vectors can generate a large number, and that's what we say here. It's a whole space of vectors. Now a few more vector manipulations. An inner product of two vectors, and you usually write it as the inner product of A and B, two vectors, with these angle brackets around it, is a very general definition. It's any type of what you would intuitively think of as multiplication of A and B, which follows some properties. And we'll just remind ourselves what those properties are. So if you're given three vectors, A, B, and C, the first property that an inner product must satisfy is commutativity. So inner product with A and B is the same as inner product with B followed by A. So you can flip them around. Now we have distributivity. Inner product of A with B plus C, which are two vectors, is the inner product of A with B, the inner product of A with C taken separately, and then the results added up as vector sums. There's a third property which is called a positive definite property. It's a very important property for inner products. The inner product of a vector with itself leads to a vector that's greater than 0. You cannot have any element of the result be negative. Okay? And it's equal to 0 exactly when A is 0. Otherwise, it cannot be 0. Now, for any scalar L times A and the result inner product with B is the same as taking the inner product of A and B and multiplying it by L in the end. A dot product, which we will be using, is a particularly interesting form of an inner product, and it's also the most common. So given vectors A1, A2 through AN and vector B, B1, B2 through Bn, the dot product of A times B is simply A1, B1 plus A2, B2 plus AN, Bn. So you can think of this as a row vector, this as a column vector, and you're doing a vector product where A1 is multiplied with the first element, A2 is multiplied with the second element, AN, the last element, is multiplied with the last element, and then the result is summed up. It's a fairly easy thing to verify that what you see here, the dot product, satisfies all the rules here of an inner product. So building on that, we have a very important construct which we will be using as we move forward, not always explicitly referring to it, but nevertheless using it, called a vector space. We use the symbol bold V to represent a vector space. It's a set of vectors, and this is an important word which we will visit in a second, which is closed under finite vector addition and scalar multiplication that satisfy a bunch of conditions, 8 different conditions. It's just a definition, you have to remember it, and we'll be using it because if it satisfies those 8 conditions, a vector space gives us very nice properties which we can then use as we move forward in analyzing big data and trying to come to terms with how to cope with the bigness of big data and not be overwhelmed. So a very popular example of a vector space is the n-dimensional Euclidean space R to the power n, where a plane in 2 dimensions, R to the power 2, is a good example. So in R to the power n, it's obvious every element is represented by a set of n real numbers. It's a vector, and so that's the set. And now let me spend a couple of minutes, since it's not always obvious, on this concept of closure. So given 2 vectors A and B, we would say that R to the n, our example vector space, is closed if A plus B is also in R power n. So anytime you take two vectors and add them up, the resulting vector should also be in the vector space. That's called a closed system, in this case a closed set. In addition to this closure property, a vector space will satisfy a variety of other properties, and we'll walk through them slowly. So now let's take three vectors, and we'll use all three to define a vector space. U, V, and W, all from vector space V, and two scalars, alpha and beta, which we will be using in the definitions. So the first requirement for V to be a vector space is U plus V equal to V plus U for any two vectors in this space. Associativity of vector addition, we would say that it's associative if U plus V plus W, where you first do U plus V and then add it to W, is the same as first doing V plus W and adding it to U. Then the third property, which is called an additive identity. Every one of these vector spaces has an element like 0 in the numbers, in the real numbers, such that for any vector U from the vector space, 0 plus U equal to U plus 0, which is just U. And similarly, a concept of additive inverse, and this is important. For every vector U, there is a counter or a sibling vector minus U, such that U plus minus U is the 0 vector. These are requirements. If a set of vectors does not satisfy any one of these requirements, you cannot call it a vector space. Okay? Just to clarify, I've used this term. 0 is simply the vector where all elements are 0. And similarly, the additive inverse of U has the same components with the sign changed, basically. Okay? Element by element. Property number 5, associativity of scalar multiplication. So what we mean here is if you do alpha times beta times U, which it is alpha, beta, take the product first, then do the scalar multiplication with U. Distributivity of scalar sums. If you do alpha plus beta, take the sum first and multiply it with U, you could as easily do alpha times U plus beta times U. And distributivity of vector sums, alpha times U plus V, where you do U plus V first and multiply by the scalar, is the same as alpha U plus alpha V. And scalar multiplication, which is basically by an identity element, the unit element 1, where every one of these vector spaces has a unit element, a scalar, is 1 times U is U itself. So that's the full set of, those are the 8 conditions I mentioned that constitute a vector space if all 8 are satisfied, along with the closure property that we discussed earlier. Then we have a concept which is very important, building on this, the concept of dependence and independence. Given a set of vectors, we would say that they are linearly dependent, provided one of the vectors in the set can be written as a linear combination. Remember, a linear combination from a few minutes ago is simply using, of two vectors, let's say, is a scalar times the first vector plus another scalar times the second vector. So now we're talking about a set of vectors being dependent, provided one of the vectors in the set can be written as a linear combination of the other vectors. That means somehow you could generate vectors from this set from its siblings in the same set. Whenever no vector in the set can be written, no vector, as a linear combination of the rest of the vectors in the same set, then the vectors are said to be linearly independent. So here is a simple exercise for us to think about, which you can solve in a few, using this definition in a few minutes. So let's say that we had three vectors, examples. U, which is the vector 1, 1 in 2 dimensions, V, which is the vector -3 and 2, and W, which is the vector 2 and 4. And it's useful to check and see if we can convince ourselves that these are indeed, all three together, are linearly independent using the definition written just above here. So continuing, and with that background in mind, given a vector space, we can now talk about subspaces or subvector spaces. So let's say that you have a set of, what's a vector space? It's a set of vectors that satisfies a certain condition. And the condition is that it be closed, and there were these 8 properties that you had to meet. Then a subset of vectors from V is called a subspace, provided that subset satisfies all the properties of a vector space. Will every subset satisfy this property, or will some pass and some fail? First, to answer that, let us consider 3 dimensions and look at the space R cubed. Then the origin by itself satisfies the conditions 0, 0, 0. Any line passing through the origin satisfies this condition. Any 2-dimensional plane passing through the origin will satisfy it. Finally, all of R cubed satisfies it. Something for you to check, not very difficult, condition by condition. However, here is something that's a useful exercise which may hand out in one of the worksheets. Would the unit cube, a cube with side 1, with its center at 0, 0, 0, be a subspace? So it's useful to check and see if you can convince ourselves as a hint to satisfy this whether it's closed. Because if it's not, it cannot be a vector space. So the idea here that what people have been doing with vector spaces is to think of the 3-dimensional world we live in and then abstract it away algebraically to n dimensions, many, many dimensions. And think about the smallest way you can represent these n dimensions. And how do you do that? By a set of vectors, obviously. And the most common way of doing that representation is something called a basis. So given a vector space V, a basis is defined as a subset of vectors in V that are linearly independent among themselves, but also significantly they span V. That is, combinations of these independent vectors can give you every vector in V. And these are called basis vectors. A vector space V can have many different bases. It doesn't have to have one basis, but there are always, and this is an important result in algebra, any basis for any vector space must have the same number of vectors, and that number is called the dimension of V. So if you take a plane, it's 2 dimensions, any basis for that must, by definition or by requirement, have exactly 2 elements in it. So if you take, as I said, 2 dimensions and consider the following example vectors u and v, you have the vector 1, 0 and the vector 0, 1 that forms a basis, because it's very easy to see that every point in the 2-dimensional plane can be generated by a linear combination of 1, 0 and 0, 1. So basically you would write it as a scalar times the first vector, another scalar times the second vector, and its dimension is 2, because why? In this basis you have two vectors, u and v. There's an interesting concept. While you can have all different types of bases, it doesn't always have to be 1, 0, 0, 1, which is intuitive. You can think of what is intuitive, the 1, 0, 0, 1 basis, as what we call a standard basis. So in 3 dimensions, it would be 1, 0, 0, 0, 1, 0, 0, 0, 1. So a standard basis is a basis where every vector in it has exactly one element with the value 1 and everything else with the value 0. If you take the plane R2, then you have vectors 3, 2 and 2, 1 they are a basis, and you can convince yourself of the two-dimensional universe or the two-dimensional world. So any vector in R2 can be generated as a linear combination of vectors 3, 2, and 2, 1, but it's not a standard basis because it does not satisfy this property at the top of the slide. But then you can change from one basis to another. Algebra allows you to do that. So if you are given the, a vector space and it has many different bases, and so what you can think about is if S is a basis for V, then every vector can be expressed where S is this vector with elements V1 through Vn, okay? Then every vector in vector space V can be written by definition, because that's what a basis does. Vector V can be written as C1 times V1 for some constants or scalars, C2 times V2, etc., through Cn times Vn. So this will be a generator that will give you every vector in the vector space V. So you can think of, and this is how you would interpret this geometrically, if you have elements C1 through Cn, these are essentially the coordinates of V relative to the basis S. These coordinates are easily understood if you, of course, think of the standard basis, because when you think of the standard basis, the two axes you normally have, x and y, in two dimensions, let's say, your coordinates would directly give you the vector. But you may have non-standard basis, and if you could similarly therefore have a different way of writing out this coordinates C1 prime, C2 prime through Cn prime in some other basis S prime. So let's take a close look at this. So here is a nice clean standard basis B, 1, 0, 0, 1 are the basis vectors. And now you have this other basis for this two-dimensional example, B prime, which has these two vectors, 3, 1 and minus 2, 1. And these are two different bases for R2. So the change of basis from B prime to B can be written nicely in a clean form algebraically by simply writing it out, writing this particular basis. You want to go from B prime to B as this matrix. And you now, let's take an example. You have the coordinates of a vector V relative to basis B prime. Let's say these coordinates are 2 and 1. And now you want to figure out what the coordinates would be with respect to B. So you start out with B prime, and these are its coordinates. And the coordinates of vector V now translated into B would be essentially this matrix borrowed from these two basis vectors times the coordinates in B prime. And you would get, if you simplify that, 4, 3 as the new coordinates. And the change of basis is therefore in algebra a transformation which is based on a product of a matrix with a vector. So to think of this as a simple example, geometrically, you had the original basis, minus 2, 1 and 3, 1, and you had this particular example, a vector in it, 2, 1, which we could see in the previous instance could be generated from these two vectors as a basis. But now our standard basis, what we normally see when we look at two dimensions, is the x-axis and the y-axis. This would be 1, 0 and 0, 1 are the two basis vectors. So if you did the translation into this basis, the resulting vector would be 4, 3. So you can go back and forth between vectors like this and see how you can translate a vector from one basis for a vector space to another basis for the same vector space.
Stopping recording.